nuclear weapons have played a critical role in preventing conflict among major powers since the end of World War II. Ensuring the safety and reliability of this nuclear deterrent is an essential part of national security. But how can scientists test and evaluate the U.S. nuclear stockpile in the absence of nuclear testing? In this episode of the National Security Science Podcast, we'll learn all about new experiments to ensure the United States maintains a safe, secure, and reliable nuclear stockpile. It all starts nearly 1,000 feet underground. I'm Brenda Fleming, and this is the National Security Science Podcast, a spin-off of National Security Science magazine at Los Alamos National Laboratory. We bring you stories from the lab's weapons program, stories that show how innovative science and engineering are the key to keeping America safe. This is the third and final episode on nuclear testing, and today we will explore the sophisticated ways scientists are gathering information without detonating nuclear bombs. When the United States halted nuclear testing, the program of science-based stockpile stewardship began. The term stockpile stewardship refers to approaches to ensure the reliability of nuclear weapons and nuclear materials such as plutonium by using computer simulations and physics experiments rather than nuclear testing. Today, Los Alamos National Laboratory and its partners are building some of the newest tools for stockpile stewardship at the Nevada National Security Site. The National Security Science magazine team traveled to Nevada to visit an underground laboratory where the latest developments in stockpile stewardship technology are underway. Here's Jill Gibson with a look at what we saw.
U1A is an underground laboratory where scientists conduct experiments that they can't do anywhere else. On the surface, there's not much to look at, just a handful of trailers. Our visit begins in one of those trailers, where we meet Roger Rocha, the Vice President and Chief Operations Officer for the contractor that manages and operates the Nevada National Security Site.
You're going to go underground and you're going to see where we do a lot of the subcritical experiments. Just picture trying to put a $1 billion accelerator down there. And that's why it's great that you're here and you're seeing it. Because when you see it on a piece of paper, you see pictures, right. It does not do it justice. Mm-hmm. When you stand in the accelerator hallway, you gotta remember all of that dirt had to come out of that hole, right? Yeah. I mean, it's huge, and you're 1,000 feet underground. So go to a happy place.
The facility consists of about 2.5 miles of tunnels, where the national labs, including Los Alamos, are building machines to carry out subcritical nuclear experiments. Subcritical means the experiments use small amounts of plutonium without creating high-yield explosions. This technique allows scientists to learn more about the U.S. nuclear weapons stockpile without conducting actual nuclear tests. We're eager to see the facility, but first we have to watch a safety orientation video and get our personal protective equipment.
Feel free to ask questions. You'll find the downhole environment surprisingly comfortable and fully ventilated, with well-lit rooms, concrete floors, high ceilings, many work areas, and lunchrooms.
U1A facility manager Vince Gomes issues each of us steel-toed boots, hard hats, and safety glasses. Completing the ensemble is a flashlight and a breathing device called a self-rescuer.
This 2-pound device, which is placed over the mouth and nose, will be used in the unlikely event of an underground fire. Any type of underground fire will generate poisonous carbon monoxide gas.
Now we're prepared, and more than a little nervous. We enter a large steel cage that will be lowered on a giant spool of cable attached to a hoist. Gomes shares a few facts before we begin our descent.
Okay, so 965 feet underground we're going. If you saw the stratosphere, it's about that. The shaft, or the hoist, the H-hoist goes at 880 feet per minute. So you get about a minute ride.
The cage doors close, and we plunge into darkness. No one speaks as we begin our trip down, accompanied by the eerie whir of the hoist. a little more than a minute, it feels much longer. The cage doors open. We are greeted by the roar from the ventilation fan.
So that's where talk about the H fan, that's where it takes suction out.
Gomes leads the way as we move deeper into the maze of tunnels called drifts. We see large rooms with high ceilings where tons of dirt and rocks have been removed. It's so big, though. I mean, it doesn't feel like you're deep underground.
No, this is really a laboratory.
The largest of the drifts will house Scorpius, a $1 billion, 1 million pound radiography accelerator named after a constellation.
This is where the Scorpius machine basically going to take up almost the whole length of this drift. It looks pretty big here, but it's going to be jam-packed full with equipment. Also, due to the weight of the machine, so you see the alluvium, which again, a sandy, it's not really a rock. We're going to put cement, and it'll be about 6 feet. So imagine about 6 feet of cement, and then the Scorpius machine.
Scorpius will generate pulsed X-ray photographs that capture images in tiny fractions of a second to understand the late stages of the plutonium implosion. It will unlock secrets that scientists have pondered for decades and will provide answers to how plutonium and weapons age. How do you get it in here? Do you bring it down in pieces?
Yes, it'll be in several sections. In fact, right now they're figuring out how to do that. I have a guy whose only job is to figure out that hoist and how to use it and get, to coordinate that effort. They have building facilities to go test each unit before they bring it down, and then they'll assemble it down here.
Currently, about 70 people work underground at one time. But when the facility is fully operational, it will support a staff of 300 people and 3 active test areas. Los Alamos National Laboratory physicist Steve Sinte explains the experiments that will be performed here.
Subcritical experiments are the intentional firing of an experiment that has nuclear material and explosives. This test bed is specifically designed to provide multi-pulse radiography. The key technologies that are enabled are the actual radiography of a plutonium assembly, which will be essential for characterizing the stockpile in the future. In this facility, you get the closest to actual performance parameters of the stockpile.
As we continue walking through the tunnels, we pass heavy equipment and teams hard at work drilling new chambers. Gomes explains the complexity of ventilation and the process of distributing power and water underground.
We have a high pressure system that comes down from the surface, and that's where the heat is exhausted to good old Nevada, and then we distribute chill water throughout the facility. Of course, Nevada, we don't have a lot of natural water lying around, so we have to bring it in trucks. And we have what is called a utility water system, which brings water down from the surface. The problem, the adventure is that we're 965 feet below. So if we just ran water straight down, the water pressure would be about 500 pounds. And this is what is known as an uninterrupted power supply. So this does 2 things for us. It provides, clean power for the diagnostic equipment, and it also provides a battery backup for about 30 minutes. So if we lose power, we can, right in the middle of the experiment, we don't interrupt it, still get the data.
One of the advantages of underground testing is the ability to carry out experiments in 6-foot wide vessels and then permanently bury the vessels within parts of the facility. These areas are called entombment drifts.
The vessel will go about right where you're standing, and then we do the experiment, and then the vessel is going to be wheeled out through there, and it'll go right, and I'll show you the entombment drift.
This is going to come down here, start there, and then what happens, we entomb the vessels, fill it out, and eventually we'll fill this whole area with vessels and entombment. It's probably about 30 years worth of vessels. Now, I mentioned that it's going to get blocked off, so if you look at that mesh area, there's going to be a plug that's going to be put there.
The high-strength carbon steel containers weigh 15 tons and have port-like windows around the sides.
This is a 6-foot vessel right here. It's going to be HSLA 100, which is a high-strength carbon steel, about an inch thick.
Each time a vessel is used, it contains multiple experiments.
The other thing to note is that when we do an experiment, they actually put a lot of samples in there, so we're really doing like 6 experiments at the same time.
Los Alamos physicist Chris Frankel leads us into the control room.
So this is where we control the experiments in the Cygnus test bed.
And we will control the other 2 test beds.
So when you do a shot, is there just 1 or 2 people in here,
No,
or
it's
the whole
not.
room full?
So there's 2 TNF folks, there'll be a diagnostic manager, there'll be myself and Steve behind the dais there, and then there'll be a federal employee from the audit field office, and those are sort of the required people. And then we usually fill up the other chairs with people who just want to hang out and
Be part of it.
VIPs and see what's going on, right?
And then you're watching on the display.
All these will essentially be are sort of red, green. None of the actual data from the experiment comes here. That stays in the classified area. Hopefully everything turns green by the time we get down to T equals 0. The computer is monitoring several hundred channels that are part of the experiment.
Next, we visit the area where the Zeus test bed is under construction. Sinte explains the unique role of this part of the underground lab.
So the purpose of the Zeus experiment, this is a test bed that's solely focused on reactivity as the key primary diagnostic that this facility enables. And so Scorpius has a linear accelerator for the X-rays that provide the pulse X-rays. What Zeus will have is an external neutron generator. So it'll stimulate the experiment with a pulse of neutrons, 1 pulse, at a key time in the experiment, and it will, that doesn't change the critical nature of the experiment, doesn't make it more critical or less critical. That's all based on geometry and time. What it does though is it extends the reactivity. So we can observe that gamma ray signal longer and learn more about the experiment.
Finally, we wrap up the visit with a look at an accelerator called Cygnus. The device was named after a constellation that got its name from the Latin word for swan. Cygnus has already generated a great deal of information about plutonium implosions. Because this is a working laboratory, we have to leave our recording equipment outside.
Does everyone have a Q clearance?
Yes.
Q?
There's a lot to see deep beneath the ground at the Nevada National Security Site. Between construction and testing, U1A is a busy place.
The facility opens on a typical day somewhere between 7:30 and 8:30.
Most of the staff members spend at least 8 hours a day underground. But after our brief visit through the 2.5 miles of tunnels, we're eager to see sunlight. We re-enter the steel cage for our trip back up to the surface and bid goodbye to U1A.
Thanks, Jill. Over the past 3 episodes, we have explored the history of nuclear testing, the moratorium on testing, and the new devices that scientists are now using to ensure the safety and reliability of the nuclear stockpile without conducting nuclear tests. We'll conclude our special series with some comments from Los Alamos National Laboratory historian Alan Carr.
We're still testing. We're not doing full-scale testing. We don't have that tool available, but we have a lot of other tools, including less than full-scale explosives testing. See, nuclear testing was a wonderful tool, and it really, really was. It was also the world's biggest shortcut. It could get you to where you wanted to go really fast when you could just go out and do a full-scale nuclear detonation in Nevada or in the Pacific or somewhere else. We didn't have to understand all the details of a nuclear weapon and how it functions. Well, now we have to know a lot more than we did before. And so the technical challenges that we have today are, I think, as exciting as they have ever been. I'd also say that they are as important as they have ever been as well. And if you don't believe me, go read the newspaper. Go online and read headlines instead. It's a dangerous world out there.
Thank you, Alan, and thank you for listening to the National Security Science Podcast, stories from the National Security Science Magazine. You can find the full magazine at lanel.gov/magazine, and for more great stories from Los Alamos, including several other podcasts, video series, and interactive stories, visit discover.lanel.gov. Finally, thank you to everyone who made it possible for the National Security Science Magazine team to visit U1A and learn about the future of stockpile stewardship research. Truly a fascinating glimpse of how better science equals better national security.